Now you know that we can graph real numbers on what we call a Cartesian plane, where our vertical axis represents y coordinates and a horizontal axis represents the x coordinates. And we use that when we graph things in science and other applications, where the x-axis or the horizontal axis represents our independent variable and the vertical axis represents our dependent variable. So in the same way that we can graph real numbers, we can graph complex numbers, but with a little difference. Okay, that the plane that we use is set up in the same way as a Cartesian plane, okay, and its adaptation of it is called the Argand plane, or the Argand diagram, named after a fellow by the name of Argand. Now, the difference is that our vertical axis represents our imaginary part of a complex number, and the horizontal axis represents the real part of a complex number. So that's where it can be handy if we represent our complex number in terms of x plus yi, x being our real part and y being our imaginary part. Now, if we were to look at a few of these points, okay, we've got these points here that are plotted on this Argand diagram, and they represent these complex numbers. So the point A, you'll notice we come across 6 units on the x-axis. In other words, 6 units along the real axis. Okay, so that's 6 to the right because our real part is positive 6. Our imaginary part is 3, and so that's positive 3, and so we come up 3 units on the imaginary axis, and so it has the point 6, 3. B is the complex number 2 minus 3i, and so plotting that on the Argand plane, we have our x-coordinate, or on the real axis, is 2, and so we come across 2, and then the y-coordinate relating to the imaginary part is negative 3i, so we come negative 3, so we come down to negative 3. C is the complex number negative 7i, so it's going to be on the imaginary axis and down to negative 7. And D is simply the real number negative 2, so we plot that on the real axis at negative 2. And then E is the complex number negative 4 plus 6i, so we go across to negative 4 and up 6. So that's plotting complex numbers on a regular using rectangular coordinates, or Cartesian type coordinates, where we have an x and a y coordinate. Now we can also plot them using polar coordinates. Okay, and so that requires us to get our complex number in polar form. Polar representations of complex numbers involve specifying a magnitude, which is a distance from the origin to the point where it would normally be plotted on the Argand diagram using our rectangular coordinates. Okay, so we specify the distance from the origin to that point, and we also specify the angle that the line from the origin to that point. We specify the angle from the positive x-axis. So the angle specified is similar in a way to when we're working with trigonometry and the unit circle. So we measure from the positive x-axis, so in this case the positive real axis. Now the distance, as you can see, is quite simply worked out using Pythagoras' theorem. Okay, the magnitude, or the distance from the origin to the point, is worked out using Pythagoras' theorem. So if we have our complex number as x plus yi, okay, so z equals x plus yi, then we've got our x coordinate and our y coordinate on the Argand diagram. And so if we want to find the length of this line from the origin to the point, that corresponds to a complex number, then we just use Pythagoras' theorem of the square root of x squared plus y squared. And that's shown here, written here as this formula. So you'll notice the square root of x squared plus y squared equaling the absolute value of z. Okay, that is commonly referred to as the modulus. So it's written as the absolute value of z, or we commonly also use r. Okay, and you'll probably see me use that a little more rather than the absolute value of z. Sometimes it's written as the absolute value of x plus yi, so you can see that really means the same thing, or mod z, just short for modulus. It's always positive because we're just talking about a distance. Okay, it's just a magnitude, so it's just going to be a positive value. Furthermore, we have the angle, which we need to define the polar representation of the complex number. So we have our magnitude. We also need direction. Okay, and so we use the angle from the positive real axis, or the positive x-axis, similar in the way that we would with the unit circle and trigonometry. So it's called the argument. Okay, so the argument is what we refer to as this angle here from the positive real axis. And so we use theta, or it's also denoted by arg z. Okay, now it's important to note that by definition our angle there is taken to lie within this specific range, negative pi to pi. And this particular value of theta that is within that range is known as the principal argument. And so we would denote that as arg z with a capital A. Okay, so even though we can represent it using any angle really at all, by definition it's within that particular range. Now the point P, x, y, has a horizontal distance from the origin of x units, okay, we've already seen that, and a vertical distance of y units. So by applying our regular right-angled trigonometry, we can find that those horizontal and vertical distances can be defined in terms of our modulus and our angle theta, or our argument. Okay, our horizontal distance x, okay, our horizontal distance x is equal to the modulus r times a cosine of our angle theta. The vertical distance y is found by multiplying the modulus r by the sine of our argument, or angle theta. Okay, and so we can write our x plus yi in a different form, and this is the polar form that we were leading up to. X equals r cos theta and y equals r sine theta, so that x plus yi is r cos theta plus r sine theta times I. And then by taking our modulus as a common factor out, we have r outside of cos theta plus I sine theta, and abbreviated to z equals r cis theta. But that's not the only polar form. If we have a look here, this is called Euler's form, but it's also another way to write polar form, because we have here our modulus r and our argument theta, and it's r times e to the I times theta, and that's Euler's form. That's also commonly used. Now, we've already noted that the modulus of a complex number given in rectangular form is z equals x plus yi. That's found by using Pythagoras' theorem. Okay, we've already seen that. The argument of a complex number given in rectangular form is found by using basic trigonometry. Okay, and if we just scroll back and have a look at our little graph, we can see that we've got our hypotenuse here, which is our modulus, and our angle theta. We've got our x coordinate and our y coordinate. And now if we know our x and y values from the rectangular form, z equals x plus yi, then we can find theta by using our tan ratio, because tan of theta is equal to the opposite over adjacent, and our opposite side is going to be the imaginary part, y, and our adjacent side to the angle is the real part. So whenever we find our angle theta, our argument, we first look at what it is in this quadrant. Okay, we ignore any positives and any negatives, and we just think about it in the first quadrant. So it's just like finding our basic angle for trigonometry, our first quadrant angle. Okay, so tan of theta equals y over x, or our real part over our imaginary part over our real part. So if we just scroll back, we can see that here, tan theta is our imaginary part over our real part, or theta is arctan, or the inverse tangent function of y over x. So we'll stop there for this video, and we'll look at some specific examples of converting from our rectangular form to polar form in the next video.